Hey there, chemists. In the previous video, we looked at how we can make carboxylic acids. Now we're going to look at what we can do with them. What are some reactions that we can do to these acids? We'll start off with how we can turn them into esters. This specifically makes a methyl ester, so this is a very specific reaction that we're going to start off with. The methyl ester means you just get an O-methyl directly attached to the carbonyl, and involves a reagent known as diazomethane. It's a very reactive little molecule that you have to make in situ, meaning you usually make it right before you use it. To show how this works, let's redraw the carboxylic acid. And diazomethane is actually zwitterionic. It's got a negative formal charge on the carbon and a plus formal charge on one of the two nitrogens. So the first thing that happens is it acts as a base and deprotonates the acid. So you get a carboxylate. And then the product, or I should say the intermediate, is a methyl directly attached to the azo group. And we're almost there. How do we get from this pair of intermediates to the product? The carboxylate that we just made will act as a nucleophile. It will attack the methyl, and it will kick out the nitrogen as a leaving group. Now you can see why this is so specific for making a methyl ester, because they only have reagents like this with methyl directly attached to the diazo. And you spit out a nitrogen molecule. Very clean reaction. There's no byproducts that trouble the reaction mixture when you're trying to purify this. So that's for making specifically a methyl ester. What if you want to make another type of ester? That's what we can use the Fischer esterification for. The Fischer esterification has an alcohol reacting with an acid to make your ester. And believe it or not, you learned this reaction back in 10th grade chemistry. If we just pan over for a second and pretend we're back in 10th grade chem, your chemistry teacher taught you the reaction of a carboxylic acid back in the days when you were likely not using line structures quite so much. There is a simple carboxylic acid and an alcohol. I'll actually use the alcohol that's in this example, which is ethanol. Looked so big and scary back in 10th grade, and now we draw it so much more simply in Orgo. And I remember teaching this, you would draw a box around the part that you remove, and there it is. You lose a water molecule, and then the carboxyl is attached to the alcohol group. You get an ether, what looks like an ether attached, but it actually becomes an ester. And you just wrote esterification on your notes. Without any arrow pushing, but that is indeed a reaction that they even show in the New York State Regents exam. We're a little bit more sophisticated, so we're going to draw line structures for this and use what we know about our modern arrow pushing methods. This is in acid, so we're only seeing positive charges. Your first step is protonation of the carbonyl. So you get an oxonium. And then the alcohol sees this oxonium and attacks. Draw an arrow from the alcohol oxygen to the carbonyl carbon, send that pi bond up to the oxygen. So far so good, only positively charged intermediates. And here we have this. Now remember we said we make an equivalent of water in this. We want to somehow have a net generation of water, and that's going to come from this intermediate, but we can't lose an OH as is. It needs to become a water molecule. So we'll do a proton transfer, aka an acid base. I'm going to do it intramolecularly. In all likelihood, it could happen intermolecularly with another solvent, etc. We've seen this so many times lately. So here it is again. Now one of those OHs is a water molecule directly attached to the carbon. And now it can leave. And at the same time as it leaves, a lone pair from either of the above oxygens can come down to give a more significant resonance contributor. And we are one step away from the product. In fact, we can use the water that just left as a weak base to take away that last H. This is highly reversible. And that's how you get your product. So you regenerate acid. Okay, so just like all acid-mediated reactions, first step add an H+, last step remove an H+. And just to remind you that you saw the reverse of this mechanism before, I'm going to put reversible arrows at all these steps because it is highly reversible. In fact, we did this mechanism in the reverse way yesterday, or I should say in the previous lesson, where we started with an ester and we did a hydrolysis to make the carboxylic acid. If you go back and look at the previous lesson, you'll see exactly that. Okay, there's 3 other reactions of carboxylic acids on your notes for today. These mechanisms are all a little bit more unique, so I actually have mechanism templates. And what I would like you to do is hit pause and see if you can simply add the curved arrows to each one of these to show how you make a acid chloride, a ketone, and an alcohol from these 3 extra reactions. Try that now. Okay, let's see how we did. So the first one is a reagent you've seen before, thionyl chloride, which changes an OH to a Cl. That's true even if it's not a carboxylic acid, but it's just an alcohol. We saw that last semester for alcohol becoming alkyl chloride. Easy to remember because now we have acid becoming acid chloride. How do the arrows work? Well, first the carbonyl oxygen forms a bond with the sulfur, and then the sulfur-oxygen bond goes up to the oxygen. We then reform the sulfur-oxygen bond, and one of the chlorides leaves, so I have an arrow from the oxygen to the bond, and then from the bond to the Cl. And then we form a new bond between the chlorine and the carbon, so draw an arrow from the chloride to the oxonium carbon here, send its pi electrons up to the oxygen. We get a neutral intermediate. I'm just going to highlight that. When you're doing lengthier mechanisms, can be confident you're on the right track if you run across a neutral intermediate. Also worth reminding, we're neither in acid nor in base, so you see a mixture of positive and negative charges in this particular reaction. Now, this is the last batch of steps here, and this is probably the hardest part to figure out. To reform the carbon-oxygen double bond, a lone pair on this OH donates to make that pi bond, and it spits out this SO2 molecule, and the sulfur-chlorine bond breaks, and that's how I get a chloride and an equivalent of SO2, which is just a gas. Lastly, we need to lose an H+. Looks like we're making HCl, so I'll draw an arrow from the chloride to the H, break the OH bond. So that's how you make an acid chloride. Now, how to make a ketone. This is with a lithiate. Also works with a Grignard. Remember, not a cuprate, though, because cuprates don't react with ketones. Now, last semester, we said organometallics were actually incompatible with carboxylic acids, and that's not entirely true. You just get a different reaction than maybe the one you want. The first part is an acid base. You kill an equivalent of your organometallic just by removing the H on the carboxylic acid. So that's the first equivalent. So you made RH, whatever it is. If this was methyl Grignard, you just made methane in a very expensive way. But once you have the anion, a second organometallic can attack that carbonyl carbon, and now you absorb the electrons. You get a uniquely unstable dianion intermediate. You get protonation of both of those oxygen anions, so you get what's called a hydrate. Looks sort of like an acetal or a ketal, but we have OH attached to each, and hydrates are not stable. These are very transient, and in the slightest acidic conditions, you will protonate one. It becomes a water molecule the water molecule leaves, the OH donates a lone pair, you get an oxonium, the oxygen takes that H, and then you regenerate your ketone. You regenerate your carbonyl, and that's how you make the ketone. Okay, lastly, how do we make an acid into an alcohol? The main reagent we'll talk about is LAH. There are some others that do this. Borane acts as a reducing agent for acids as well, but I'm going to show it with lithium aluminum hydride. We actually drew out lithium aluminum hydride here, and what we just saw in the lithiate mechanism will happen similarly here. A hydride acts as a base, and you first use an equivalent of hydride to take that acidic H off of the carboxylic acid. So we actually lose an equivalent of hydrogen gas. That's where this H minus and this H plus combine, and you get an H2 molecule. The aluminum hydride left behind can act as a second source of hydride, so draw an arrow from the aluminum H bond to the carbonyl carbon and send that pair of electrons up to the oxygen. And at this point, the aluminum is actually what picks up the oxygen. We have to completely lose one of these oxygens. So to do that, one of the oxygens donates a lone pair to reform a pi bond, and then the other one breaks off. It sort of looks like we're losing an O negative as a leaving group, but it's not leaving by itself. It gets coordinated to this aluminum, and you get an aluminate species. Notice there's a lithium counter ion here, just along for the ride. It's just a reminder to show us that charge is balanced. We usually don't draw these inorganic ions in our mechanisms. I decided to show it here just to highlight how the charges are taken care of, because this otherwise looks like a very unusual mechanism. The aluminum hydride can actually donate yet another source of H. So draw an arrow from the aluminum H bond down to this intermediate aldehyde. You'll notice we're at an aldehyde intermediate, and LH reacts with aldehydes. That pi bond goes up to the oxygen. And then there's one more arrow. The oxygen anion picks up an H+, and that's how you finally get your alcohol. So that lithium aluminum hydride used 3 of the 4 hydrogens that it started with to give us this alcohol in the end. Okay, so those are just a handful of reactions starting with carboxylic acids. There's some practice problems on the back, and moving forward, we're going to look at things that we can do with these other acid derivatives like chlorides and such.